Look up at the night sky, and it feels eternal. The universe is about 14 billion years old. Modern humans and our early ancestors have inhabited Earth for roughly 6 million years. Cosmically, this is a fraction of a second. But the true test of our species lies much further ahead. The ultimate goal is figuring out how to keep humanity alive for the next 100 billion years. A common assumption is that we have plenty of time. We imagine Earth is safe for another 5 billion years, right up until the sun runs out of hydrogen and expands into a red giant. That timeline is dangerously optimistic. This chart maps the sun's expected energy output over time. Notice this sharp 10% upward spike at the 1 billion year mark. The sun is getting hotter, and long before it swallows the Earth, it will roast it. An increase of just 10% in solar radiation will push Earth's average temperature near 120 degrees Fahrenheit. The oceans will begin to boil, turning into thick, suffocating steam clouds that trap greenhouse gases and permanently choke out complex life. Sitting quietly on Earth and hoping for the best is a mathematical dead end. To stretch our timeline into the deep future, we have to start actively re-engineering the cosmos. The first major test is outrunning that expanding sun. Since we cannot protect the Earth from where it currently sits, the engineering solution is to physically pack up our entire solar system and move it. The Shkadov thruster is a massive, incredibly thin, spherical mirror positioned over a star's poles. Massless photons from the sun hit the mirror and bounce back. Over 1 billion years, this continuous thrust pushes our solar system thousands of light years away. Alternatively, we could intervene in the sun's internal physics before it reaches the red giant phase. By building a megastructure called a Kaplan thruster, a massive star lifter, we could systematically siphon away the star's hydrogen and helium mass. Removing that mass lowers the core pressure and halts the aggressive fusion reactions. We would effectively shrink our raging sun into a cooler, stable red dwarf, a type of star that burns predictably for trillions of years. Successfully navigating this first bottleneck means using the sun itself as a propellant, turning our entire solar system into a mobile vessel capable of steering through the galaxy. If we manage to survive our star, the next threat arrives at the 4 billion year mark. Our Milky Way galaxy is currently on a direct collision course with our neighbor, Andromeda. Because space is remarkably empty, direct stellar collisions are mathematically unlikely. Instead, the real danger comes from the surrounding chaos. The merger will trigger intense waves of supernovae, flooding the region with lethal gamma radiation. Here we see a map of the impending galactic merger. The strategy is to use our stellar engines to steer our solar system away from the chaotic, dense galactic core, carving a path outward to the sparse, relatively quiet outer rim. We survive the collision through strategic avoidance. We park in the galactic suburbs and wait a few billion years until the violent merger settles into a single, massive elliptical galaxy. By the time the universe hits the 10 billion year mark, the landscape will be profoundly hostile. Expansion will push galaxies so far apart they become invisible to one another. The era of bright, star-forming regions will end, leaving behind a cold void populated largely by fading white dwarfs and black holes. This extreme energy deficit means civilization must evolve. To harness the astronomical amounts of power needed to survive, humanity would need to graduate to a Kardashev Type 3 civilization, a society capable of controlling the energy output of an entire galaxy. The ultimate survival blueprint is the Birch planet. This cross-section shows a solid spherical shell constructed entirely around a supermassive black hole. Tapping into its energy, this structure could comfortably house 10 to the 30th power inhabitants, 100 quintillion times Earth's capacity. However, maintaining biological bodies requires constant caloric intake and narrow temperature ranges that a cooling universe cannot easily provide. So, to reduce our energy footprint by orders of magnitude, we may eventually host human consciousness within Matryoshka brains, digital civilizations powered by the faint, final radiation of a dying star. Outliving the stars demands extreme measures. We have to strip away everything familiar and anchor our very existence to the heaviest, most powerful gravitational engines left in the dark. Look 100 billion years down the timeline, and the Earth we know is completely gone. Our current biological forms and the pale blue dot we evolved on will be ancient history. We will exist either as lines of code in a cosmic server or as physical beings walking the metallic plains of an artificial megaworld, bathed in the distorted light of a captive black hole. The universe is not a permanent sanctuary. It operates on a strict expiration date, driven by merciless physics that will slowly snuff out the light and heat we rely on to exist. But biology doesn't have to dictate our destiny. Our long-term survival isn't found in a pre-existing home, but in the megastructures we build to replace the stars.